Artificial Intelligence and Machine Learning for Amateur Radio Operators. I'm Van Warren. In traditional programming, we write procedures that are executed on data to produce answers as output. In machine learning, we train models to recognize features. We then run those models to do that recognition in a process called inferencing. Training is more expensive than inferencing, but it only has to be done once, at least in principle. Here are some branches of machine learning, or ML. An important distinction in ML is supervised versus unsupervised learning. In supervised learning, we can perform regressions or classifications. A regression is a model that predicts a value given an input. For example, predicting tomorrow's temperature given the past week's temperatures. A classifier partitions labeled points into groups or categories. This can be done with lines or with curves, usually polynomials. Unsupervised learning is when an ML model looks for patterns in unlabeled data. It discovers clusters and patterns on its own. A great example of this is Principal Components Analysis, or PCA, which discovers the most significant features in the data and can sort those features by importance or frequency. Ensemble learning is where multiple models are combined to improve predictive performance, like getting lots of second opinions. There's even a proverb about this. In the multitude of counselors, there is safety. In supervised learning, models are trained on data that contains features that are labeled. The model learns to produce the label given the feature. Deep learning uses many layers of neural networks to solve more difficult problems. Convolutional neural networks are used to process visual data and imagery. Convolution is the process of sliding a filter over an input image to detect features like edges or, with more layers, specific shapes. Any data that can be represented as an image can be processed using a CNN. My dissertation explored using a CNN to read instruments in an aircraft cockpit. Reinforcement learning is where an agent is rewarded for making a correct decision. Reinforcement learning is used heavily in robotics and in gameplay. It has its origins in the work of psychologist B.F. Skinner and the discipline of operant conditioning dating back to the 1930s. It dates even further back if one considers the work of Pavlov and his dog. Now you know. Each type of neural network is a creature in a zoo of possible configurations. Perceptrons were the first kind of neural networks, invented back in the 50s. Recurrent neural networks, LSTMs, and GRUs handle time-varying data, like stock market data. Autoencoders and variational autoencoders transform and translate data. Large language models, or LLMs, like ChatGPT, had their origins in autoencoders. There are a wide variety of configurations, each of which has its own utility. You may recognize Markov chains, deep convolutional networks, and generative adversarial networks, or GANs. GANs are the basis for image generation techniques like DALL-E, Stable Diffusion, and Midjourney. In the beginning, or shortly thereafter, we had the equation of a continuous line, an explicit formulation where y equals mx plus b. But what if we don't have the slope m or y-intercept b? Given 2 points, we can compute the slope m and the y-intercept b. With that in hand, we can compute y for any position x on the line. But what if we have 3 or more points? Then we're going to have 3 or more possible lines. Eventually, we will have more lines than points. You can prove this to yourself by drawing 4 points to get a square, then connecting the corners to get 6 lines. The number of lines grows as the square of the number of points. Regression combines the points to create a representative line or curve. Classification partitions labeled points into categories. It is upon these two ideas that machine learning is built. A great place to learn about classification is playground.tensorflow.org. This tool allows us to visualize how a neural network learns to solve classification problems. Let's start with the basics. We have a simple pattern here, a circle, and our goal is to teach the neural net to classify points inside and outside the circle. We'll use just one hidden layer with 2 neurons. Think of neurons like decision makers analyzing different parts of the data. On the right, we see this learning curve, which shows us our test loss and our training loss. Notice how it learns this simple task relatively quickly. We can also see which neurons are most heavily involved by the thickness of the tracks between them. So we have a set of features, we have a hidden layer, and we have an output layer. Now let's challenge our network with something tougher, a spiral pattern. We haven't changed the network yet. It's still simple. Let's see how it copes. Well, as expected, our model is struggling. it can't find a clear boundary because it doesn't have enough neurons to understand the complexity of the spiral. So it trained rather quickly, but it didn't give us a model that did a good job. Now let's add layers and neurons to give the network a deeper understanding. With more neurons, you can see the network is getting a little better at bending the decision boundary to fit the spiral. What you're seeing here is a machine actually thinking. It's as though you're looking at the brainwaves of the learning curve. Now obviously we haven't gotten a perfect result, but we've gotten a much better result than we had previously. Now let's try changing the activation function to a rectified linear unit, which is a lot like a diode. And here we really get a good result, and not too much time. And notice that if we'd stopped before it was completely learned, we might have gotten a much less optimal result. This stopping technique can be used to get a result for less training time, but it bears the risk of not training to completion. You can experiment more with the many varieties of functions that there are, and it's really fun to see how a change in the sophistication of the model affects the speed of the learn. Another interesting thing is that each neuron gets a job, and some neurons aren't very heavily used and some neurons are really important. I'll let you play with this on your own, and I urge you to do so. It's because it's incredibly interesting. Also remember to add noise, because sometimes adding noise can prevent you from overfitting the model. Before we dive into the receiver operating characteristic and its associated confusion matrix, consider the aerial combat situation during World War II. Aerial combat was a critical aspect of war, and both the Allied and Axis powers relied heavily on their air forces and radar. The ability to accurately identify enemy planes and distinguish them from friendly planes was crucial to the success of a mission. Now, the ROC parameters are these. There are only 4. There are true positives, or correctly identified positives. There are false positives, incorrectly identified positives, true negatives, correctly identified negatives, and false negatives, incorrectly identified negatives. In a conflict scenario, a false positive treats a friend like a foe. A false negative treats a foe like a friend. I'll let you ponder which is worse. ROC parameters and diagnostics. A true positive is a diseased patient who tests positive for the disease. A false positive is a healthy patient who tests positive for the disease. A true negative is a healthy patient who tests negative for the disease, and a false negative is a diseased patient who tests negative for the disease. The confusion matrix tallies the Cartesian products of true and false with predicted and actual, and sums the rows, columns, and number of items in the matrix as a parity check. Here we have true positives and false positives, false negatives and true negatives. It's a little easier to understand this if we populate it with actual values. These are the mathematical definitions of all of our model metrics. Accuracy is the fraction of all predictions a model gets right, both positive and negative. Precision is the fraction of positive predictions a model gets right. Sensitivity, also known as recall or the true positive rate, is the true positives divided by the quantity true positives plus false negatives. Selectivity, which is also known as specificity, is equal to the number of true negatives divided by the sum of the true negatives and the false positives. The false positive rate is the number of false positives divided by that same quantity. The area under the curve is a measure of the model's performance. 0.5 indicates a completely random or chaotic result, while 1.0 represents a perfectly accurate model. So here we have the old friends of precision versus significance, accuracy versus precision, and bias versus variance. Accuracy measures how often the model is correct in both positive and negative predictions. Precision measures how often the model predictions are correct. Bias is error from assumptions in the learning algorithm. It causes underfitting, where the model doesn't capture all the nuances of the data. Variance is error from too much complexity in the learning algorithm. It causes overfitting, where the model learns too much, including the noise. On the left, we see underfitting, where trends in the data are not well represented by a single line. In the center, we see a balanced fit, where the trends are followed. On the right, we see overfitting, where we have fit the model to the noise in the data as well as the trends. The sensitivity versus selectivity paradox refers to the trade-off between a test's ability to correctly identify true positives, sensitivity, and its ability to correctly identify true negatives, selectivity. High sensitivity may reduce selectivity and vice versa. The bias-variance trade-off is the challenge of simultaneously minimizing two sources of error in predictive models. Bias error is the error due to simplistic assumptions in the model, and it is quadratic because it increases sharply when the model is oversimplified. Variance error arises from the model complexity. Too much complexity leads to fitting noise. Reducing bias typically increases variance and vice versa. So we have to find that happy medium. So here we have finally the receiver operating characteristic curve itself. It's nothing more than a plot of the true positive rate versus the false positive rate, and it depicts the trade-off between sensitivity and specificity. So let's look at three quick examples of receiver operating characteristic: diagnostic medical test, detecting drones, and a radio receiver. For a diagnostic medical test like a CBC, someone might go into the emergency room and the physician would order a CBC to be drawn, which is a complete blood count, so they can characterize or screen or rule out things that might be or might not be wrong with their patient. So here we see, even for the routine CBC, that there's quite a bit of variation in the accuracy of the different parameters that a CBC can produce. For example, in the green, we have the mean cell volume with an area under the curve of 97%, so we can really believe that result. But if we try to deduce the hemoglobin, we're only going to have a 0.75 area under the curve, which means we're going to be less certain about the exact value of that hemoglobin. Similarly, one can monitor drones and determine the make and the model of the drone by the style of RF command it receives on the XM band. Here we see the ROC curves for each of 6 different drones, along with the noise and the averaged receiver operating characteristic. So let's think about a radio's receiver operating characteristic. After all, that's where this all started. The sensitivity is controlled by the RF gain, which amplifies weak signals. And we can also think of it as the squelch. Selectivity is controlled by the IF filters, which isolate specific signals. A ROC curve would show the balance between weak signal discrimination versus noise. So homework 1, if you're interested, is to contrast the ROC curve with the signal-to-noise ratio. And if you use ChatGPT-4, it goes really fast, and you can also check your answer with another LLM called Claude 2 100K that's at poe.com. The second homework, if you so choose, is to draw the receiver operating characteristic for your receiver or transceiver. Okay, now we're almost at the end, and we're to the place which is the most exciting part, and that's the neural net heard round the world. And that neural net heard around the world was called the transformer architecture, and it's in a paper by Google called Attention is All You Need. And it enables a long context to be processed instead of just the short little snippets. This ability to process a very large context and reason by analogy has resulted in some very interesting properties. And I won't go through this because I'm going to show you a video in a second that gets in a little more detail. The transformer architecture gave rise to the large language models that are having so much success now, like ChatGPT, Claude 2, and Bard. ChatGPT-4 was trained on 13 trillion tokens at a cost of about $200 million. The trick is excluding irrelevant information during queries, which is done by prompting. So let's look at how we can prompt these models.